Hey guys, it's Greg. Today we're going to be implementing the DBSCAN clustering algorithm in Python and Scikit-Learn. Now, two notes before we start this. This is not going to fully explain the algorithm in particular. If you do want that, you can check the video description and I will have a link there for a separate video where we don't talk about the coding. And point number two is that this is going to be a full tutorial on how to actually get good results with this, not some 2-second Scikit-Learn copy where you just fit a model. We're going to do the whole thing over here and how you would need to do this in practice and everything you need to understand. Okay, so let's get started. We will do import pandas as PD. I think I can even do one more zoom for now. Import pandas as PD, import matplotlib.pyplot as PLT. We're actually going to be using plotly as well, although for now matplotlib is easier. Import numpy as NP. And this is in Google Colab, by the way, if you guys didn't know, but you can use whatever site or IDE that you want, as long as you get this Google Colab California Housing Train.csv file here. I'm going to be using it. So we'll actually load that right away with df is equal to pd.read.csv. And then that file is located at sample_data/California housing train.csv. And then we'll just output the data frame df. Okay, so we just loaded that CSV as a pandas data frame. And basically what it is, you've probably seen it before, but as a quick overview, these are many different rows in the data frame. We have 17,000 rows, and each of those rows has 9 columns. Each of these rows represent a particular area in California, which is marked geographically by its longitude and its latitude. And we have different descriptions of those areas in California, such as the median age of all of the houses there, the total number of rooms in those houses, the total number of bedrooms, the population, and so on. I'm not going to go over everything, especially because in this video, I'm not really going to use everything. We'll use a couple different pieces, starting with the latitude and longitude, because a really nice way to graphically represent or show what clustering does is to use two-dimensional graphing data. And this will be very clear in a moment. We'll get lat long as a subset of the data frame with df sub. We grab those columns, latitude and longitude. Okay, and we'll just for now separate that into two different variables. Lat and long, we need to do long with 2 G's, is equal to df dot latitude and df dot longitude. Okay, so now that we have that, we'll just do a quick plot of plt.scatter with long and lat. It has to be in that order so that we get what California actually looks like. Since each of these points are an area in California with its longitude on the X and its latitude on the Y, this is actually going to show California. And so we don't have, if we fully painted in California, you would kind of fill in all the cracks and get the whole area. But these are just different areas in it. Okay, so why is this important? Well, we're going to do a DB scan on these two columns here, or on these two different variables. And so we can get loaded up with that right away. It's not overly difficult to fit a DBSCAN model. We do from sklearn.cluster import DBSCAN. Okay, so that's their class for building and fitting DBSCAN algorithms. And we'll do X because, as always with machine learning, you usually have some matrix or something that's kind of like a matrix, maybe a tensor. We have for now X is equal to lat long, which is that subset of the data frame, dot to numpy. Okay, so that would mean that x dot shape better be, sorry, I must have mixed something there. I just put two double equals, or a double equals. X dot shape here, it's going to be, X is going to be a numpy array with that same number of rows, 17,000, and 2 columns because it's just the latitude and the longitude. Now to fit the model, which I'm actually just going to put in here instead, we do grab it in a variable. We do dbscan underscore cluster underscore model is equal to dbscan, and then we set 2 different variables. We set epsilon and we set the minimum number of samples. If you don't know what those are, well, you can kind of get along with this video if you don't really want to completely fully understand what they do, but I will give a little bit of a hint if you haven't seen how the algorithm works in particular. For now, I don't actually want to set anything, and so we'll just agree with their defaults, whatever they are. dbscan, and we dot fit just X. And it's just X because this is an unsupervised learning algorithm. We're not trying to do some function that maps an input to an output. We are just learning something about the input space. So we .fit X. Now, if we output our DBSCAN cluster model, we will get just DBSCAN. Okay, it just fit a model and it didn't really say anything interesting. We fit a model. What is interesting about this, but it doesn't tell us, is that we have DBSCAN underscore cluster underscore model dot labels underscore. That's probably the most important thing for any clustering algorithm. The point is to label different things, label all of the points as a given cluster. And so if we do, I'll just output that for now. It's an array. And if we convert this to a pandas series, we'll actually add it to our data frame. If we do df subcluster is equal to that labels, and then if we output the data frame, well, that shows that we basically put in a new column on the end there. That is each of our labels. And so I'm saying cluster because it's what cluster or what group it was assigned to, what label it was given. And it was assigned to each of the points. We have 17,000 of these clusters. We have one for every single point. And that's great because what it allows us to do is, well, we've labeled every single point and now each of them belong to some particular group. We can actually look at the different distribution with df subcluster dot value counts. And what this does is this is saying that 16,982 of the points were assigned a cluster label of 1, 8 were assigned a cluster label of 0, and 10 were assigned a cluster value of -1. Basically what the -1 means is noise or equivalently outliers. It's basically saying each of these 10 points, they didn't really fit into any particular cluster. It's not like they're all part of this -1 cluster. It's basically saying that they are all outliers or all noise. And we'll see that visually in a bit. Okay, but anything that's not the -1, it's considered to have found a part of a particular cluster according to the parameters that we gave in the algorithm, DBSCAN, with whatever epsilon and min samples we gave. Again, if you don't know what those are, it doesn't really matter for now. So basically what we have is the values of each of the different clusters. And these ones are noise, and the other ones are part of some actual cluster. Well, what we can do is, well, graph, where we have the same plot as above in matplotlib. Actually, we're going to convert to Plotly because it's a lot easier for this type of thing. But now we want to give each different cluster a color. And Plotly also does a really good job of, you can hover over each point and see exactly what it is referring to. So we can just grab Plotly with import plotly.express as px. And we'll do fig is equal to a px.scatter with x is equal to long as before, y is equal to lat. And most importantly here we set color equal to the df subcluster. And basically, it's best explained by just showing you what this does. Plotly's really smart about this color thing. And since we set it like that, it's going to say that each of the values that have the same color, it is going to pick a color for them. And so that'll be consistent. So each of these ones, you can hover over and see that the blue ones here are color of -1. We can actually see that in this scale over here as well. I should really zoom out a little bit so you can see it better. But yeah, all of this yellow stuff, this is considered the one cluster. And apparently we had some tiny little cluster over here. Now, it turns out that this doesn't really make all that much sense. And it's kind of up to, either a visual discretion or what we'll see later as some metrics as to what makes a good clustering model. But, this doesn't really make that much sense. Like, if I could get that all of these are maybe a cluster because it's like inland stuff. And then we have some of the outskirts, which are maybe outliers. But I really don't like that. It's just that there's this little kind of cluster over here, supposedly. And if this is your first clustering experience, then basically all we did is, according to some unsupervised learning algorithm, we colored each of the points, or we assigned each of them to a group, depending on the DBSCAN algorithm's parameters in this case. And it doesn't really make sense, all of these different, the 3 different clusters that it has. Technically only 2. We have this cluster in yellow, this cluster in pink, and then these are outliers. What I would have preferred to see is, I don't know, just something different. And there is, if you go to Scikit-Learn's page, they have a really nice page on the different clustering algorithms and their effects. But I can tell you that DBSCAN can do a better job of what we see here. And what I am going to show you in particular is that this is not going to get a good score on what we call the silhouette score in Scikit-Learn. Okay, because this is an unsupervised learning approach, we don't have really any way of really easily verifying like how good this model is, at least one that makes really good sense. What I'm going to use without explanation is something called the silhouette score, which attempts to do that. And it's a little bit complicated as to what exactly it's doing, but it is a score from -1 to 1, which is 1 is really, really good, and -1 is really bad, and 0 is also, not very good as well. Okay, so if we do from sklearn.metrics, we import silhouette score, and I'm just going to write it as SS because that's really irritating to write over and over again. And if we do SS, if we pass it, I should probably zoom in a little bit more again. We pass it our input matrix X and the cluster labels that were outputted, df subcluster, that's a different way of getting those labels that we got. It's going to output a score for us, and it actually takes a little bit of time to compute that. It gets 0.26, which is okay, but you could definitely get better for this cluster model. Like this, it makes a little bit of sense, but it's not amazing. So what do we do? How do we try and adjust this? Well, DBSCAN, you can play with two different components. You can play with epsilon, which is the distance that marks a core point, and you can play with min samples, which says how many points are required for something to be a core point. Epsilon also does slightly more than that, but it's not really a big deal. As I said, I don't want to explain the full algorithm here. You can check it out in my other video, and that will explain. Okay, so most importantly, we do need to play around with epsilon and min samples. And we could do this randomly for now. We could go back to where we changed that. Sorry, it's a little too far. We didn't change anything here at all. And their defaults, whatever they are, we're going to change epsilon and min samples. So if we do epsilon, maybe we'll set it equal to a smaller 0.2. And we could also set maybe min samples to be, I don't know, 15. And let's run that again. Okay, it's not going to look all that different for now. What we should see is a different number of clusters. Okay, so here's all the different distributions. There's 84 get assigned to the 0 label, 15 get assigned to the 1, 9065 to the 2, and lots of different ones. What's important for DBSCAN, as you see here, is that we don't choose beforehand the number of clusters that are going to be outputted. And so that is kind of figured out automatically by the algorithm, depending on those parameters that you gave. So it got a lot more clusters, and we can run this again. And what we see now is something that, makes a lot less sense than it did before. I really don't like this at all. Yeah, this doesn't make a lot of sense for California. And so what do we get according to a silhouette score? Well, marking our visual guess, it is about the same, I guess. According to this metric, it's still not very good. And I guess it thinks that it's okay. But I'm telling you, I really don't like this result. Now, although we may not get a perfect result for any data set, and I'm not trying to pretend that this is something that you can really get a super awesome result on for California, what is important is that we can optimize this somehow. And to do that, well, we usually use in machine learning some sort of a grid search. And you may see some other techniques for finding epsilon and min samples in DBSCAN. But what's easiest to code, even though actually what's coming up coding, it's going to be a little bit confusing. I apologize for that, but it is really, really useful. So stick with me on it. We're going to optimize via a grid search on epsilon and min samples. And if you don't know what a grid search is, it's not very complicated. It basically just says try all possible combinations of these two lists of things. And so if we get, say, a bunch of epsilons to try, epsilons is equal to np.linspace with, we'll say, starting at 0.01. You don't want to start at 0 because you don't want 0 distance. That would not make the algorithm happy. np.linspace 0.001, and we'll go to 1, and then we'll do number of those is equal to 15, so that our various epsilons to try are these different values here. okay, so spaced evenly between 0.01 and 1, we have these different epsilons to try. We could, of course, get more or less, but I don't want this to take super duper long, and I do want to get a decent search as well. We can get different min samples is equal to np.a range between 2 and 20, and a step equal to 3. This is just something I played around a little bit on my own, and you can feel free to play with them by yourself. There's really no limit to how many different values you need. I'd pick more than one, so at least 2, and generally between 0 and 1 for epsilons. We'll actually get to that because this isn't standardized, although longitude and latitude are pretty much on the same scale, so we don't have to worry about that at the moment. We will in a bit, but still either way, between 0 and 1 is going to be probably proper, and min samples, so some values between say 2 and 20 are decent to try. So, and I don't need an equals. Min samples, we're just going to do 2, 5, 8, 11, 14, and 17. And so a grid search is just going to try, well, 0.01 and 2, and 0.01 and 5, and 0.01 and 8, and all of those combinations. And then 0.08 with 2, 0.08 with 5. So it's just trying all these different combinations to try and get a good one. And an easy way to get those combinations is just import iter tools, and then you can do combinations. Combinations is equal to the list of iter tools dot product with epsilons and min samples. Okay, and then combinations is probably what you'd expect. It's actually with tuples, and so it's a list of the tuples of all of those combinations, as I said. So in the first column, you have all of your different epsilons. In the second column, you have all your different min samples and the combinations between those. Okay, I'm gonna exit that because it is kind of a long list. And just so that we have this, we're gonna do n is equal to the length of the combinations. And we can see that n is equal to 90 in this case. Now, this is by far the most complicated coding we're going to do, so stick with me, but most tutorials won't do this because they don't place an importance on finding an actually good model and showing you how to do this. I will show you how to get an actually good model for DBSCAN. So we can do define, get, scores, and labels. If you get confused in this, just wait it out and I'll explain everything, I promise. Define get scores and labels with combinations and x. Okay, so that combinations, you can probably guess we'll be passing in this combinations over here, and x, that's kind of the same or possibly a different matrix as before. It should be a NumPy array, which represents a matrix as an input. So we'll start with these two empty lists. Scores is equal to empty list, and all labels list is equal to an empty list. This is going to be a list of scores that is going to be for each DBSCAN model that we try. So we're going to have 90 of those because we'll be trying 90 combinations. And this is going to store all the different lists of labels. So the first component of this will be the labels associated with the first combination. And the labels associated with the second combination would be the second element. We're just going to try many different combinations of DBSCAN, or we're just going to try many different DBSCAN models with each of those combinations and record its main results. Now what we're going to do is first a for loop, where for getting I and epsilon and num samples enumerate the combinations. Okay, if you haven't seen enumerate before, basically it's just the best of both worlds for iterating through something. This is a list of tuples, and so we get the index starting at 0 and then going up until the length of it -1 as usual. And this we get immediately access to epsilon and num samples, which is that particular combination that we're going to be iterating through, since we're enumerating through the combinations. Now we'll make a model, DBSCAN _ cluster _ model is equal to DBSCAN, and then epsilon is going to be equal to epsilon, whatever epsilon we're iterating through, or whichever one from the combination we have, which is dependent on our combinations, and we're doing a grid search. So we're going to be, each time we get a model, we're going to be storing its results, and we're going to be trying to find the best one. So min samples, it's going to be that min samples that we have that we're iterating through as well, which will be num samples. and then we'll dot fit with x, just like it is above. We'll get the labels, which is equal to the DBSCAN cluster model dot labels underscore, just like it was before. We'll convert that to a set. Labels underscore set is equal to the set of the labels. And then what we want to do to count the number of clusters, well, first it's going to be just number of clusters is equal to the length of the labels set. Except then to get the actual number of real clusters, because if something's assigned to -1, then it's not really a cluster, it's just noise. The number of real clusters is going to be reduced by 1 if -1 is in that set. So if -1 is in the labels set, if we actually labeled anything as noise, then we're just going to decrease num clusters by 1, minus equals 1. Okay, so why do we need that? Well, it's because we don't really want to make or even spend time on models that make really no sense. And it's a little bit up to us as to what makes no sense. But I don't want to do if num clusters is less than 2. So this is even disregarding the noise already. So this basically means if we've only made actually one real cluster, I don't like that model. So I'm not even going to consider it if this is true, or something that's a little bit up to our discretion. Technically, there should really not be an upper bound on a number of clusters. It's not really realistic to say, hey, if there's something bigger than say like 50 clusters or so, this is getting a little bit complex. Now, again, many people would disagree about this practice. This is not some set in stone practice. But if we're getting something massive for this particular problem, I'm just going to ignore it. Now, what we're going to do is, if this is true, then what we want to do is ignore it. To ignore this properly, we will still append some garbage into the scores, because we're still trying to calculate, this should be the score for this model, but we're going to ignore it, so we're going to add some noise here. And we'll also match this up with all labels list dot append bad. So we're going to append, again, just some garbage into this list, which basically just says, ignore this score, ignore this set of labels, because we're not using this model. If we wanted to, we could make this nice printout, which I'm actually just going to copy in, because it's not super relevant. If we do c is equal to that tuples there, we can output this nice string, which basically says, hey, I want to still just write some output to see what we're doing. Okay, so now what we want to do is basically, since in here we have a continue, which basically just says if something's wrong here, we're just going to go over the next iteration, grab the next epsilon and number of samples. Well, if we down here, we actually do care about the model. And so that means we should have some score, since we already made the model up here. So we'll scores.append the actual score that we got, which is computing that SS with X and the labels. That's how we did it before. And we'll also do all labels list dot append with the labels. Okay, so now here we added the score for that set of parameters and we added the labels. Now we're going to add a nice print here as well. I am actually going to copy this in here as well because it's not super important, but again, I'm just gonna really skip over that. Okay, so now what we want to do is return things that we actually care about. What do we care about? Well, we probably care about the parameters that were best, the labels that were best, and the score that was best. Okay, so what parameters got the best score and what labels were associated with that model. The reason we need to actually get the labels right now, instead of running the model again, we could technically just extract the same parameter, the best parameters, and then run that model once more to get the best one. Well, the reason we want to actually extract the labels is because DBSCAN is not deterministic. Due to the way it sequentially makes something kind of at random, a cluster, well, that's going to make it not necessarily get the same output every time. And so we want to get the labels that were associated with it the first time that it ran. So what do we need to make sure it's best? Well, we'll do best index is equal to the numpy.argmax of the scores, because that says which index maximizes the scores. That's the one we care about. Now we can basically just index everything with this. We'll do best parameters, or our epsilon, best combination basically. Best parameters is equal to combinations sub the best index, because that's the combination that has the best score. Now we can do best labels is equal to all labels list, and then give that the best index again. So those are the best labels that are associated. And finally, we'll also get the best score, which is just going to be scores sub best index. Okay, very long function, I know, but it is done after we simply just return this dictionary, which I'm going to do as return. We'll get the best epsilon, which is best parameters sub 0. It is going to be the best min samples with best parameters sub 1. Since this thing is a tuple, we need to get sub 0 and sub 1. Best labels, which is that labels there, and best score, which is those scores there. So we're just returning a dictionary, our results basically. Now what we can do with this absolutely massive function that probably no one else is really using is best dict is equal to get scores and labels. That's what we call this function up here. Get scores and labels. Technically it gets a little bit more than that, but get scores and labels on combinations and x. Now if we run this, you will see that it takes a pretty long time, and I probably will skip to the end, but it shouldn't take too long. And I made sure that this doesn't take a massive amount of time on Google Colab. It takes a little bit to do a grid search. That's understandable with machine learning. Sometimes you do have to wait a little bit of time. But with our output, you can see some stuff being shown. When I write moving on here, that's our output, or that's our printout here that says, hey, it has this many clusters. This is why we're moving on, and we're just adding trash, and we're not actually thinking about that one. I will just resume the video after that's over. So as you can probably see if you followed along, even if you didn't here, you can see after it hits a point, basically after the epsilon, and pretty much after the epsilon it gets too high, past 0.64 or so, it's just getting way too many or way too few clusters. It's getting one pretty much every time, and so it pretty much gives up. But there is a lot of different options in here, especially in around this range where we have the epsilon. Where is it? Around this combination here. Around epsilon is 0.15 or so with min samples, different values. We're getting some pretty decent scores in here. We have a 0.32 and a bunch of negatives as well. It definitely varies, but you can see we are beating our previous score of I think it was 0.25 when we tried it on our own. We're getting many different scores that are higher than that, which is a good sign. That's the best we can really hope for. Okay, so let's extract our best dictionary, because we got that stored in a variable. Best dict is, the best epsilon is 0.29, and that is not true. Sorry, that is true. I was thinking that was the score. Best score, we found a 0.4066, which is much better. These are our labels associated. We'll grab those, and these are our parameters. Epsilon is 0.29. And best min samples was 14 associated. Now let's just go ahead and override what we had before. So we'll do df sub cluster is equal to now the best dict sub the best labels. Really all that we actually need is the labels, although we did store this other stuff because it's kind of interesting for you and I to see what values were actually making this work. And maybe if you wanted to further kind of do a closer grid search around these areas, you could do that. But really we're just going to take these labels and we will again look at the df subcluster dot value counts, looking at the distribution that it was outputted. And it outputted this. That's a nice amount of clusters usually. Something like in the 5 or 6 range is quite often a nice number. And minimal noise, a little bit of noise, 202. But if you do have outliers, like they should be classified as outliers. And a nice different distribution. So what's good about this is there's not some where there's like so few, like we're not getting like 3 or 4 points. And it's not like all dominated by just one cluster. We are getting mostly dominated by 2 clusters and then some various other things. So just like before, we are going to make our graph, and it's the exact same. So I'll just copy it in. Fig is equal to px.scatter x with, actually that should be long and lat, I think, because I believe my code is actually wrong over there. We should be outputting it as, yeah, long and then lat, not lat and then long. Sorry about that. So long should be over here and lat over here. And then we output this again. And we see something that maybe makes a little bit more sense. You know, I think this color, it's definitely better than one of the earlier ones we've seen. And that first one, you know, I think that first one didn't really make too much sense. Here you can kind of see some distribution over here. Another cluster sort of makes sense in the middle. It seems to have, I'm kind of surprised it found one over here and that wasn't classified as just pink. Yellow, I can definitely see why they're just kind of its own cluster in the middle over there. And everything over here is classified as an outlier, which is really what we wanted to see, because the stuff on the outskirts, that kind of did strike me as either maybe it could be marked as its own cluster, or if it's not, then at least it should all around the edge be kind of classified as noise. And some of the other stuff in the middle here definitely just seems like that one you wouldn't really associate that with anything other than an outlier. Okay, so this is just kind of showing you that you can actually optimize to make a visual cluster model that actually makes sense. Now, a big question here is, well, what if you have more than two variables? Because you can't really color this, and you can't really visually look at it well if it's more than two variables. Well, you would actually just do the exact same thing that we had before. You wouldn't really need to change anything at all because we optimized this for the silhouette score. However, one thing that you should change, even in our example, it probably wouldn't do anything, although it doesn't hurt because it's latitude and longitude. I said it earlier, you should scale your variables. And so the important one, or at least it's really obvious to show that this is a problem if we look at the full data frame. So I should really be, I don't know why I'm not fully zoomed in here. If you look at DF and you did try to do a clustering on this, well, housing median age is generally very small. You're not going to get a housing median age bigger than like 1,000, or probably not even close to that range. But if you have total rooms and total bedrooms, you'll definitely be in the thousands. And other variables here, especially if there's money involved, money is usually a very large number. And so median house value, if you had that in there, you have some variables that are on a very small range, like 0 to 100, and you have other variables that are like 0 to like 100,000. And so basically what would happen if you just put that raw into the algorithm, well, it's just going to really ignore those smaller pieces, because the distance between, say, this point and this point is like 15,000, but the distance between like this variable is only 4. And so it's going to say like, hey, I really don't care about this 4 distance when I have to maximize this, when I have to worry about this 15,000 distance over here. Okay, and just to show this graphically, I will pick a couple of variables that explains it very well. We'll do a plt.scatter on df.total rooms, that's one column, and df.housing median. Actually, yeah, I'll just stick with that for now. It's good enough. Okay, so here you can see it's kind of all slanted over here, but most importantly, look at the range of the axis, as we just explained, 0 to 60 or so, and 0 to 35,000 or so. The DBSCAN algorithm would be completely dominated and generally just confused by these different columns here. And I can show that if we were to do x2, so just getting another matrix here. x2 is df with those two columns, total rooms and the housing median age. And we converted that to NumPy. And we'll just show x2, not that we really need to show that. That's x2, a different matrix. And we will, since we have that awesome function from before, that's why we put in so much work to get this great function, we can just do best dict2 is equal to get scores and labels, calling that function. If I can type it, get scores and labels with combinations and x2, then we should be able to, actually I will let that run, and then while it's going in a new, okay, it's not even letting me type. So basically the point here, it's moving on every time. It just finished because it didn't really do much of anything. It kept making these models, but it kept having here's 0 clusters. Or this is 863 clusters. And so it's very, very confused here. You see, most of the time we're not getting any clusters. And that's because our scaling is really messed up here. And so if you look at, which I tried to do, best dict2, we're stuck with bad. Okay, we have a best epsilon and a best min samples, which is the first one because that's associated with garbage. And that's because literally all of it was garbage. There was not a single cluster model that really made any sense. And so if we do go ahead and scale our variables instead, from sklearn.preprocessing, import standard scalar, x2 scaled is equal to standard scalar dot fit transform. We don't really need to keep the transform, so I'm just going to do a fit transform like that and not worry about it after. plt.scatter x2 scaled will show all of the first column there, and then all of the second column. Just a different way of showing we're just scaling the variables, and then we're using the standard scalar in particular, and then we are going to graph those. So this is the first column, second column, all the rows, and the second column. plt.scatter that. It looks the same here. It's still going to have that shape, but if you look at the range here, it's much, much closer. Still not perfect, but much closer. And so this is 0 to -2, between 2 and -2, or maybe -3 and 3. And this is about -1 to about 16. So again, not perfect, but they are much, much, much closer to each other. And that basically says to the algorithm, hey, we're going to treat these relatively the same as we can get. And now what we can do is just that same thing as above. So I'm going to copy this exactly. I will remove that. That's way too much writing. Best dict 2, I could make it, we'll just make it best dict 3. That's a 3. And then this should be, the only change that we have to do is x2 scaled. And let's let that run. Now what we're going to see is sometimes it still runs into trouble. We don't expect these clustering algorithms to be magical, but hey, index 5 here, we did get num clusters with 32, 54, or sorry, 34. And so these are looking not so bad. And since it's actually working again, I will jump to the end of it, since this is going to take a little bit. Okay, so we're all done over there. And what's nice is there's many different scores that actually were not too bad. And I'm not really concerned about the actual score, although we will take a look at it. We can take a look at best dict, what is now best dict 3, and we see these different options. And what we can go ahead and do is, I'm not going to overwrite any of the columns because we're just about done here, but we can take a look at the new coloring. And so we will just make a new fig equal to the px.scatter with x is equal to x2 underscore scaled from 0, sorry, all the rows, and then the first column. Y is equal to x2 scaled, what? Sorry, colon, first column, and color is equal to best dict 3 sub the best labels. Okay, we have those labels stored in there that we got from our optimization, and we should just be able to do a fig.show, which might not make perfect results, but it should make something. Okay, so this actually kind of makes sense. We have all of this stuff over here got assigned to the 0 cluster. All of this stuff over here, just these 4 points, got assigned to that 1 cluster. And then we have some outlier over there, which is really nothing. So not to say that you can make some clustering that really, really makes sense for anything. And you can judge that by the fact that, yes, this best score, well, actually, it thinks that the score is very good because, you can see it does kind of picture good. Whether that means anything, it's kind of hard to tell, and that's up to you. That is a good silhouette score. Since we did scale the variables, we at least got something. And so the lesson is that you should always scale your variables unless you're purposely trying to make a mismatch and to try and treat one variable more than another. Most of the time, we're not trying to do that, and you want to treat them as well, letting the algorithm figure out what's most important to really think about. Okay, so that's the idea. I think it's pretty cool. DBSCAN is much different than k-means because it is able to say all of these ones. Actually, it's mostly in going to be shown in this California piece here. K means you would have specified the number of clusters, or maybe done an elbow method to figure out what's the best number of clusters. But either way, it would have kind of done, hey, this is an area, this is an area, and this is an area. Whereas DBSCAN allows you to have these little pieces and flagged noise as some of the outside stuff. It's a very nice algorithm, and I hope you learned a lot about how to use it. You can feel free to copy that function that I made and scale your variables and use it, because it will work very well, and you can compare them via the silhouette score method on what is best. Most people genuinely will not show a tutorial that actually shows you how to make a good model in DBSCAN. You could also, I believe, you should be able to use any clustering method. You just would change the clustering method in that. And if you wanted, you could build your own sort of class where you had, you could specify the clustering method that you wanted, maybe the different distance metric, since we did use the Euclidean distance by default. Most people would use that, and you could do something cool with that. I hope this video was helpful. If you are listening to this right now, please drop a like, because it took a lot of effort to put together. And yeah, have a great day, guys. I hope this was helpful. See you later.